about the general properties of stars, but I will start with a particular star that is well studied, and once again, mentioned that several times, the Sun is just a star. It's our star, it's important for us, but it's a star. And actually it's a very average star, nothing very particular about the Sun, as we will see next week. But it's very close to us, so it's very easy. That's not very easy, but it's easier for us to study it in details. So we'll take it at a particular case. However, the properties that we'll derive today will be extended from next week when we start talking about stars in general. So today is the Sun, the king of our solar system. Well, you're probably all familiar with the Sun. You see it every day almost. Not really in Taipei actually, but normally it's there every day, all the time. So this is a picture taken by the SOHO probe, just a satellite from NASA and ESA, so Americans and Europeans, which is constantly monitoring the Sun. And the Sun is not this yellow disk that you can see. It's actually a bit more complex than that. You can see from that picture that there are lots of features already visible from the Sun. First, the surface of the Sun looks granulary, a bit like a skin of an orange. And you see that there are places where things are far brighter and lighter in color, and places where it's a bit darker. And it's not very visible with the projector, but you see that also it's spherical. There are protuberance, things that seems like eject, like you remember when we were talking about encephalitis from satellites, when we have those magmatic ejection or cryomagmatic ejections. This is the same kind of things. You have those feature ejection from the surface of the Sun. So let's start with a couple of facts about the Sun. First, it's really an average star. Nothing really peculiar about the Sun. There are billions and billions and billions and billions of stars that are exactly like our Sun. So it's not really a particular star. So we'll come back on that next week when we start describing the properties of stars. Things what we're doing in astronomy usually is doing catalogs. We like to put things in boxes, order them very well, and study their properties. So the spectral type of the Sun is a G2. And of course, the Sun is extremely bright, but it's just because it's very close to us. In absolute, it's not extremely bright. So the visual magnitude, if you remember when we were talking about magnitudes, it's 4.83. Absolute visual magnitude, this means that the magnitude if it was at a distance of 1 parsec or 32.6 light years. 10 parsec of 32.6 light years. So you remember when we were talking about magnitudes, we bring all the stars to a given distance, around 33 light years away from us, to be fair in comparisons. Because stars that will be closer, like the Sun, will look brighter. And stars that are further, like Antares, which will look fainter. But if we put all them like they were at the same distance, where we have fair comparisons. So that's why we're doing here with absolute magnitudes. We saw that second or third lectures. So the apparent visual magnitude of the Sun is 4.83, and as we will see, it's not extremely bright. There are brighter objects. But for the solar system, it's a very, very big object. First of all, it's 100 times bigger than the Earth, so it's 110 times the diameter of Earth. And in terms of mass, it's 3,000 times more massive than Earth. So remember just that, is that if you packed up all the solar system except the Sun, all the objects, including Jupiter, etc., it's less than 1% of the mass of the solar system. The Sun is more than 99% of the total mass of our solar system. The Sun is turning on itself. It has a spin rate of 26 days at the equator and 36 days at the pole. And that's something that is very important for properties of stars. Those stars actually are more behaving like liquids, and they're turning faster on the equator than they're turning on the pole. And this will have lots of importance later today. And the density of the sun is 1.4 times the density of water. It's consisting entirely of gas. There is no solid bits in the sun. It's only gas, and mainly hydrogen, as we will see later today. We quantified the age of the sun to around 5 billion years old. It's not very easy things to do to quantify the age of stars, but we have different methods. I won't have really time to describe them, but it's the isochrone methods. Consensus about the age of the sun is around 5 billion years old. If you remember what we talked about the solar system last week, 4.5 billion years old, which is consistent. That means that the sun and the solar system are more or less the same age, which is normal. They were formed at the same time. And the central temperature, of course, we don't know that exactly. It's just an estimation, around 15 million Kelvin. And the surface temperature is around 5,800 Kelvin. And this, we know it very well. We can measure it very accurately, and you all know how, because we already talked about that. You remember? Black bodies. If you just measure the black body of a star, of any body, and you fit the Boltzmann law on it, you can derive its surface temperature. So it's just a matter of looking at different wavelengths, measuring the intensity, and then fitting this law. And if you fit this law, you will see that the sun is around 5,800 Kelvin. And remember, blue objects are more hot, and red objects are less hot, more cold. And the sun happens to peak in the visible lights. It's not a coincidence. That's because our eyes were tuned to see in the visible lights. If we are living around a star that was bluer, probably we'll see in ultraviolet, because this is where the main part of the light is coming. And you have cold stars, for instance, at 3000 K. And remember that all of us are bright. We are very bright in infrared. Remember that, around 300 Kelvin. This is the constant light we are emitting. So don't listen to people who are telling you that you're not bright. You're all very bright in the infrared. So this is the black body law, remember? And black body is defined as a body that absorbs all electromagnetic radiation, or a body that irradiates thermal radiation and temperature. So we saw that already. Just a brief reminder. You remember, if you take a iron bar and you heat it up, be careful, when it's white, it's usually hotter than when it's red. So this is the black body law, and we have seen that there is the Wien's law. It's taking that the peak temperature is proportionate to the inverse of the temperature. So the more hot it is, the more blue the black body will be. So this is the Wien's law, and the other is that the Stefan Boltzmann law. It's an approximation that the luminosity evaluates to 10 to the power 4 of the temperature. And remember, just two things to remember is that the hot body is brighter than a cool one. So the hotter you are, the brighter you are. And the hot body spectrum is bluer than for the cool one. The cool one is redder. So Stefan Boltzmann law and Wien's law. We saw that already. So in the case of the sun, we know the radius of the sun. We can measure it, 700,000 kilometers. The distance, by definition, is 1 astronomical unit, or 1.5 10 to the 8 kilometer. Mass, once again, it's approximation, 2 times to the 30 kilogram. And the light, the peak of the light of the black body, sun's black body, is around 520 nanometer. And we'll see that next week. One of the ways to characterize stars is to do it according to their color. So actually, this is the spectral type G2 correspond to stars that are yellow with this kind of lights. So you can compute, if you, as you know, the maximum of yellow light is around the peak of light is around 520 nanometer. Then you can derive the temperature directly of the sun, which is around 5,600 Kelvin. And we can estimate also the amount of light that is radiated, so the total radiated power, according to the Boltzmann's law, because now we know the temperature, and it gives us something like 4,010 to 26 watts. So your light bulb typically is 100 watts. Okay, so you see it's a very bright light bulb. And the solar flux, that means the amount of light that you're receiving per surface on the Earth. So you take 1 square meter and you count how much light we get within 1 square meter. It's something like 1.3 kilowatts. So I showed that to you already. We know a hell of a lot of the sun, mainly thanks to its spectrum. Remember, diffuse gas has a property that when you have a diffuse gas composed of a given element, when light is going through it, there will be some absorption lines corresponding to the given elements. Remember, it corresponds to the transition of the electron around the atom, or sometimes molecules as well. So if you have a very precise measurement of the spectrum of a body, like the sun in that case, then you can derive very precisely actually its composition. Of course, it's a bit more difficult than the exercise I gave to you, because in the sun there are hundreds of different elements, and all of them are sometimes very complex spectra. So when you combine all things together, that's not very difficult to decipher. So it took a long time for us to really decipher what is in the sun. So one way of representing it, so this is the two-dimension representation, or what I can do is just draw a line and just look at the flux. So when it's lighter, it's higher flux, and it's darker, it's lower flux. So we can represent the spectra in that direction. So you see, two-dimension, the lines correspond here to different absorptions. So usually in astronomy, we look at spectra this way. It's easier. So this is what we call spectroscopy. This is something that is very important in astronomy. Once again, we can derive lots of properties about object just by looking at the spectra. And usually it's done graphically. We have several methods to analyze it very accurately nowadays, cross-correlation methods and others. So mathematical methods are used to really have an accurate measurement. So the amount of radiation or intensity is plotted on the y-axis, and energy, wavelength, or frequency of the light on the x-axis. This is what we call a spectrum. And from this spectrum, so you imagine that this is a simple case. You only have few lines. So imagine that for the sun, you have many, many lines. So it takes a while to do the correlation between all the elements that are known and the composition of the sun. But we can have nowadays a very accurate measurements of it. So first of all, as you can see, this is different elements that have been detected on the sun. Of course, the list is far longer, but these are the main ones. And this is the percentage by number of atoms. So you count the total number of atoms in the sun and derive the percentage of this number of atoms that are of this element. Or you can do it mass. So different atoms will have different mass. So you can look at the percentage by mass. And you can see that immediately at 99% or 97% in mass, the sun is composed by hydrogen and helium. Hydrogen at large fraction and helium at 1/4 more or less. And this is true for any stars in the universe. And at the end of this series of lecture, I will try to explain to you that actually hydrogen and helium were produced during the very, very early stages of the formation of our universe. So you probably heard about the theory of the Big Bang. At least you probably have seen the series on TV, the Big Bang theory. So according to the theory of the Big Bang, during the explosion, during the creation of our universe, the first few minutes of the age of our universe, we have formed helium and hydrogen, and very abundantly. And then this helium and hydrogen were there, and the stars were created out of this helium. And all the other elements that we're seeing here, and we see that in a couple of weeks, in 2 weeks, when we start discussing about the evolution of stars, all those elements were formed in stars later. So you start, the first stars were composed only of hydrogen and helium. And then they produce heavier elements, they explode, they release these elements into the interstellar medium, which is reused, recycled to form new stars. And this for several generations of stars. And our sun is actually the result of several generations of stars before it. I mentioned that a couple of weeks ago. So we'll see that in details in 2 weeks. However, you can see that anyway, those elements are very minor. Their total represent few percent of the total amount of elements in our sun. But some of them are very important for us. Is a carbon. We all CHO. Okay, you're all composed of CHO. So carbon, oxygen, and hydrogen are the main building blocks of life. H2O, water. So you need helium and oxygen. Nitrogen. You remember the main part of the gas in the atmosphere is made of nitrogen. Some heavier elements, magnesium, silicon. Silicon, my computer. It's very important for our computers to have silicons. This is how the CPUs are made of. Sulfur, iron. So iron, very important as well for industry. And we will see that very briefly, but we'll see that in 2 weeks that actually in stars, you can't form anything more heavy than iron. So the list here is stopped at iron, and you can't produce anything more than iron in stars. There are a bit more complex elements in our sun. We can have some molecules that are present as well at some point. So composition of those different elements mixed together to form molecules. But it's very rare, and a very, very little amount of it. Okay. So, out of that, you conclude the sun is made of hydrogen. It's fair at 90% of a number of atoms. It's a fair assumption. So our sun is mainly made of gas. So it's a big ball of gas. And this big ball of gas is stable. That means that you need gravity is attracting all this gas in one point. And you need it to be stable. Because gravity will never stop. So if you don't stop it at some point, it keep pulling all the atoms. You probably have heard the story of black holes, notion of black holes. So black holes, it's exactly what happens when gravity is going mad. Gravity is attracting everything to it in a given point. Everything is falling into it. Even light is trapped into it. That's why we call it black hole. Light can't go through a black hole because the gravity potential is too strong. So you need something to balance the gravity. Otherwise, we end up with a black hole. And the thing that is the sun used to balance gravity is pressure, simply like that. If you take a gas and you try to contract, at some point the gas will try to expand. Remember, gas is just molecules or atoms that are moving very fast. So around us, we just constantly have atoms of oxygens and nitrogen banging around. And this velocity, the fact that all those atoms are moving fast, is creating pressure. So if you try, you all probably have done the experiment. You take a syringe, okay, to do injections. You obstruct the end of the syringe, and you try to compress it. And you will see that at some point, it's only air in it. You can't compress it more. There is a limit of pressure you can put in a gas. So this is exactly what is in action in there. So there is a constant, except that being pressure, it's thermal pressure. It's due to the heat. Because you have a source of heat at the center of the star, of the sun, which is a nuclear fusion in this case, it's heating up all the gas, and when the gas is heated up, it's very excited, so it's starting to move very fast. So it's creating lots of pressure. So in our sun, we have a constant balance between gravity, that we have tendency to pull things in, okay, and pressure that has tendency to pull things out. And actually, our sun is stable, but actually is oscillating a bit. So we know now all the stars are doing that. The limits of the sun is not totally fixed; it's actually pulsating. It's equilibrium. At equilibrium. So this is what we call the gravitational equilibrium. So you have an outward pressure that is balancing inward gravity. So remember, you have the central temperature is very high, and the surface temperature is cooler. So you have transfer of heat from the center to the outskirts. Exactly the same way we have transfer of heat within the Earth. It's very hot at the center and cooler at the outside. So you have transfer of heat as well. So actually, the structure, internal structure of a sun is quite complex because there are a lot of things in action here. So what we think, we saw that briefly last week, and we come again in a couple of weeks when we talk about formation of stars, is that the gravitational contraction got the sun to start. It's lighting its fusion. And actually the fuel that is feeding this central engine, which is more or less a power plant at the center, so the fuel that is feeding this power plant is hydrogen. Okay? And there is a hell lot of hydrogen in the sun. So actually there is enough hydrogen in the sun for the sun to burn at this rate for 10 billion years. So this gives you a rough idea of how long the sun will live. At some point the sun won't have hydrogen anymore, so it won't be able to balance anymore this against gravity. So something will happen to the sun after 10 billion years because the central engine will stop. There's no fuel in it anymore. So 10 billion years, this is the ticking clock. In 5 billion years from now, I told you that the sun is 5 billion years old. In 5 billion years, our sun will stop and something will happen. Okay, so we're talking about, I just mentioned about equilibrium, okay, gravitational equilibrium. And this is something that we all know. Every time you take a plane, every time you see a fish in his buckle, this is a kind of equilibrium. In the case of the fish, it's a hydrostatic equilibrium, slightly different than what I just showed you before. But it's more or less, it's a very good analogy. It's more or less the same forces in action. You have gravity that makes the fish go down. Okay, like us, the fish is attracted by the center of the Earth, but the fish is embedded in water, and water is creating some pressure. And as long as the pressure below the fish is higher than the pressure above the fish, then the fish is in equilibrium. Why? Because you have the weight. So these two forces, these forces add up and has to be compensated by this one. But if you have done a bit of scuba diving, you know that the more you go at the bottom of the sea, the higher the pressure is. It's normal because you have more water above you, so you have more pressure. So you know that the pressure below the fish is actually higher than the pressure above it. So that's exactly what's maintaining this fish in water. It's the balance between the pressure of the water and the gravity. Okay? So this is more or less an analogy of what's happening here. You have the balance between the pressure due to thermal energy, so the thermal pressure, and the gravity. So I mentioned that there's a lot of heat transfer, and alike this is the case in the center of the Earth, there is a structure, a very complex structure of the internal structure of the sun. So at the center we have this nuclear burning core. The nuclear fusion, what's happening, I will explain to you in a minute. That you'll have atom of hydrogen that combine together to form atom of helium. And when you do that, you produce lots of energy. And so it's very hot, the temperature is something like 15 million degrees Kelvin, and the density something like 150 times the density of water. And the surface temperature is 6,000 Kelvin or 5,800 Kelvin, and the average density is only 1.4 density of water. So you have heat transfer and you have a pressure gradient. Obviously, the pressure at the top is less than the pressure at the center. So there are two different ways. We saw that when we discussed about the Earth. There are different ways to transfer heat. And you remember that in Earth, in the core of Earth, the main way is convection, exactly like the water bubbling into your pan. And in the sun, there are two zones. One, radiative zones, where the transfer is done by radiation, exact same way that the transfer of the heat from your heater is coming to you during the winter, just radiate. And the upper limit, when it's a bit cooler, you have convections. You remember I told you about the Earth, that convection, for the case of the Earth, for the kind of temperature we have, is far more efficient to transfer heat than radiation. But here, at the core, at the center of the sun, the temperature is so high that convection is very inefficient. So that's why we have a zone of radiative transmission of the heat. So it starts with radiation, that our heat is transferred on photons. Actually, the light is transferred from the center to the outskirts, first by radiation and then by convection. Okay? So, what's happening in the center? Well, in the ancient times we call that alchemy, which was transforming anything into gold. So in the Middle Age in Europe, lots of people trying to transform iron into gold. Actually, there's a way of doing it, but it's cost a lot of energy. So you probably have heard about nuclear fusion and fission. Fission, you heard about it. Pretty bad news last year. This is the way where our power plants are fed currently. You take a big atom and you cut into two pieces and it's emitting energy. Fusion is the opposite. You take two small things and you merge them together to make a bigger one, and it's producing energy as well. So the idea of nuclear fusion and fission, or producing nuclear energy, is to change the number of protons in the nucleus of an atom. And you remember, when you change the number of protons, you change the element. Hydrogen is 1 proton, helium is 2 protons, 2 neutrons, lithium is 3 protons, 3 neutrons, sodium 11 protons and 11 neutrons, etc., etc. So this is the way our atoms are composed of. At the center, you have the nucleus, and inside the nucleus, you have neutrons and protons. And around this nucleus, maintained by Coulomb forces, electromagnetic forces, you have a cloud of electrons that is orbiting around it. So what we can do is take this big atom, cut into two. So you cut it into pieces and you end up with 2 smaller atoms. This is what we call nuclear fission. So the powers of the atomic bombs, nuclear power plants, etc., it's fed that way. You just send a neutron into that big atom, the neutron very fast, the neutron break the nucleus of the atom into pieces, and in the same way you produce another neutron and a lot of energy. That's why it's very energetic. That's why we use it to produce energy. But the reason why it's produced a bit more energy is that because if you weigh those 2 small atoms that are residuals and compare to the weight of the first big atom, there is more mass in the first one than the sum of the second one. And the difference is energy. I'll come back on that in a minute. So, this is a very famous power plant. It's the Simpsons Springfield power plant. So this is how it works. Fission, you take a big atom and you split it in 2 small atoms and you emit energy in this way. And our sun is doing the other way around. It's taking 2 protons and making helium. So 2 hydrogen and make helium out of it. So actually it's a bit more complex than that. I don't want you to remember that. I just want to remember that it's actually a quite complex phenomena. You just not directly from helium out of hydrogen. You have a chain of reactions. But something that you have to remember is this thing, it's neutrinos, and those gamma are important. These are photons. So this reaction that's telling you is at some point in the reaction you're producing light, photons, or energy. So you take 2 hydrogen, you mix them, a third hydrogen here, and you mix them together, and at some point you're emitting energy as well, or in form of light. So these, in that case, are protons, neutrons, and you have electrons. So you're producing photons, particles of light, positrons, antimatter electrons, and neutrinos, ghost particles. So in the sun, we're emitting lots of those different products, photons, positrons, and neutrinos. You remember when I was talking solar winds that are very dangerous for us? These are mainly made of positrons. Neutrinos are emitted constantly, so it's a very important phenomena. All the stars produce a lot of neutrinos, but more interesting for us, it produces lots of photons. That's why the sun is light, is bringing us light and heat. So the idea is you convert a proton into a neutron, first. This is called radioactivity. And in that case, you can produce, when it happens, you produce a positron and a neutrino. So the idea is you turn 4 hydrogen nuclei into 1 helium nucleus. Okay, let's go back here. 4 hydrogen into 1 helium. That's the idea. That's the base of it. So why is it producing energy out? So if actually you weigh 1 helium nucleus and you compare to the mass of 4 hydrogen nuclei, you realize that only the helium is less massive of around 10% compared to the 4 atoms of hydrogen. So you take 4 elements, you merge them together, you get a fourth, another element, and if you do the comparison of mass, you realize that the new element is a bit lighter than the sum of the mass of the initial elements. Okay? So there is some mass that is lost in the process. And one guy told us this. Albert Einstein tells us that mass is related to energy. E equals mc squared. This is energy, this is mass, and this is the speed of light. 300,000 kilometers per second. So you take it to the square, okay, you see that with a very little mass, you have lots of energy. If you take my mass, which I won't tell you, which is quite high, okay, you multiply by c squared, I have enough energy stored in my body to sustain Taiwan, the entire population of Taiwan, for 100 years. Okay? So a little mass, lots of energy. So this is what made that guy very famous, Albert Einstein, amongst other things, but by far E equals mc squared is his most famous quote and equation. So what this equation shows is that mass and energy are equivalent. You can jump from one to another. So mass can be converted into energy. And in the other way around, energy can be converted to mass. So what's powering our sun is exactly that. It's conversion of mass into energy. You take 4 hydrogen, you create 1 helium plus lots of energy. And nuclear reactors are going the other way around. If you take a very big element like uranium and cut it into pieces, then the sum of the 2 pieces is a bit less than the initial big. So it's going the other way around for big elements. For small elements, you take 4 small elements, 4 helium, and you merge them, 4 hydrogen, you merge them from 1 helium. There is more mass in the hydrogen side. In the other way around, for uranium, you take a big atom and you cut into pieces. There is more mass in the big one than in the small 2. So you're producing, in both ways, you're producing energy. So this is the way our sun and power plants are powered. However, fusion is very difficult to do. And lots of people on Earth are trying to create fusion-based nuclear plants. That's ideal, because you don't have radioactive residuals like the fission is doing currently. And 70% of mass of our universe is made of hydrogen. So if we manage one day to control fusion, we sell out the energy for the end of the humanity. We won't need any other energy. It's very clean. You just take 2 hydrogen and make 1 helium. How bad can it be? Problem is, it's extremely difficult to do. And the reason is because of electromagnetic repulsions or Coulomb repulsions. What happens is that what you're trying to do here is to take 2 hydrogen and smash them into each other. The problem is hydrogens are both positively, or the nucleus are both positively charged. And you remember for the magnets, for instance, there are poles in magnets. And if you take 2 magnets and try to make them close one to the other, north and north, you can't do it. It always will repulse. You will manage to do it. But if you do north and south, it's working very well. This is the same phenomena. You have electromagnetic repulsion when you take 2 protons that are positive. They just don't want to meet each other. They just reject. This is Rutherford, demonstrated a long time ago by Rutherford. So you take 1 proton and another proton, you launch them in the same direction, But eventually, when they're very close to the other, they will deviate. They will be repulsed one from the other. However, one way to go around that is to send them very fast. If you send them extremely, extremely fast, very, 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 very fast, then eventually you may be able to overcome these repulsions. It's going so fast that electromagnetic repulsion don't have enough time to act. And remember, I told you about gas. What I told you about gas is temperature is directly linked to the speed of the atoms and molecules in the gas. So the higher the temperature is, the faster the atoms and molecules are moving around. So at very, very high temperature, so the sun of the core of the star is pretty high temperature, several billions Kelvin, then the speed of the atoms is such that they can collide together. So at high speed, the nuclei come close enough for strong nuclear force to bind them together. So if you want to stick two protons together, you need to launch them at extremely high speed. And that's the problem that we have on Earth for fusion, is that the energy required for us to launch those two protons at a speed sufficient for them to merge together is far higher than the energy that is produced in the process of nuclear fusion. So actually it's not very efficient, it's not at all efficient. We need to in order to make them move that fast, we need to inject a lot of energy. And we have just little energy back compared to the energy we have invested in the solar system. So some people have done fusion, it happened, but it's really, really inefficient for us currently. So we need to find a way around. So, you know now how the energy is produced in the core of the sun. And exactly like what happened on Earth, remember it's very hot at the center and very cool at the outskirts. So you need to, the sun needs to regulate its temperature. And there are two ways mentioned. There is radiative ways and convective ways. If you look at the composition, internal structure of the sun, it's basically the same structure for all stars that are more or less the same mass than our sun. So once again, when I'm talking about the sun here, this is true for lots of stars as well. So you have a flow of energy from the center to the outskirts, lots of energy at the start. So it's generated via nuclear fusion, and then this energy has to radiate away. So there's first a radiative zone, because temperature is still very high, so it's the most efficient way for heat to be transferred. And then you have the upper layer where you have convective zones. Okay, so remember the temperature is very, and density and pressure is decreasing from the center to the outskirts. So remember, convection is exactly what happens when you have water bubbling into your pan, and radiation, this is when you heat up your pan. So, why does it matter? Well, I mentioned to you with the first picture, and this one is a very, very quiet picture. So if you remember the first picture I showed you, there were lots of those whitish spots and lots of those ejections. Here it's very quiet. And come back on that in a minute. There's a cycle of activity in the sun. But this picture is nice because you really see that the surface of the sun is not smooth at all. You really have this granular surface impression, exactly like the skin of an orange. So you have whiter spots and darker spots. And this granulation is a result of this convection I just mentioned about. Remember, the upper limit of the structure of the sun, you have this convective zone. And convection, exactly like you have only bubbles, when you boil your water, you have many, many different bubbles at the surface. Okay? So convection acts better in small cells. So what happened is that if you look at the surface of our sun and zoom in details, you will see you will have those different cells that are corresponding to convection. So in that way, you will have part of the bubbles during that direction and part of the bubbles during that direction. And the same thing around it. So this here you will have matter rising, and here you have matter sinking. And this way it's cooling down. So because it's more efficient when you work in small cells, so that's why the surface of the sun is granulated this way. That's why it's not smooth. It's because we have all those cells of convection at the surface. So, mentioned that there are two different ways for our sun to cool down. At the center, we have this radiative energy transport, and at the outskirts, you have the convection. I was telling you that radiation is more efficient, but that doesn't mean that it's actually taking less time. What's happening at the center of the sun, there are lots of gas particles. So imagine that a photon is traveling within this gas, very hot gas in the sun, is heating up lots of different atoms. So the path of the photons within this gas is not straight at all. It's actually very curved. Convection is very, very straight. So actually, it takes a very, very long time, 200,000 years, for a photon that is produced at the center of the sun to go out of the radiative zone. And then, very rapidly, it's moving out from the convective zone. Right. So, to come back on that, make it a bit more clear, you have, because of the difference of pressure and temperature within the sun, you have different layers. And one layer is radiative, that means the light would go through this layer radiatively, and the upper layer is convective. And the difference is mainly due to the fact that convection is more efficient for small gradients of temperature, while a radiative is the most efficient for big gradient of the temperature of the temperature differences. Okay. Within this radiative layer, however, the photons are not going straight. Because of the amount of particles that are in the gas that are moving quite fast, high temperature particles are moving very fast. So what happens is when the photon is trying to go through this layer, it's just bounced around every time it's hitting one of these gas particles. So if we do some numerical simulations of that, for a given photon to come from the center zone where it's produced to the outskirts of the radiative zone, it can take a very, very long time, typically 200,000 years. Okay? Right. So, how the hell we all know that? Because that's no way we can go there and take measurements directly. So, I just mentioned it. First of all, we are using lots of models, mathematical models. The same way that architects, when they want to make a new creations and build a big house or a big building, they're first starting to do a scale model. They just take the building they have in head and they make it smaller just to look at it and looks like if it works well. Well, physicists are doing the same. We just, instead of taking the sun, we put the small sun in our computer and try to simulate it. We use some models. It's always simplification, of course, because you always have life is always more complex, but it gives us good insight of how things are happening. So, for instance, the previous picture is exactly coming out of a model. So that's one way, but you still need to collect some information, some data directly. I mentioned to you that actually the surface of the sun is not always constantly at the same place. The sun, due to the equilibrium effect, which is changing a bit with time, is actually oscillating. And it's oscillating in a very complex way. It's not oscillating exactly at the same tempo everywhere. So it's constantly getting deformed. And this starts to be quite very well known. It's called helioseismology. It's exactly like having seismic wave on the surface of Earth. Remember, I told you that for Earth and other planets, the best way for us to understand the structure is to use seismic waves. Because seismic waves are transiting through the core of the Earth, and then we can learn the composition. But actually, thanks to this seismology at the surface of the sun that is constant, we can use it exactly the same way we use the seismic wave on Earth to study the internal structure of the sun. And we use something that you are already familiar with, is the Doppler shift. The fact that if you measure an object that is emitting light, if it's moving away from us, it will be redder, and it's moving towards us, it will be bluer. Remember, we saw that second lectures. This is the same thing with the sound. if you have a motorbike, you're walking on the sidewalk, a motorbike overpassing you, when the motorbike is emitting always the same sound, but when it's on your back and moving towards you, the pitch is lower, and it's moving away from you, the pitch is higher. Okay, it's meow. So there is in the museum there is a nice experiment with that actually. So by measuring difference of Doppler shift on the surface of the sun, we know which way it's pulsating and oscillating. That's very efficient. And the other way to study the internal structure of the sun is to use neutrinos. You remember I mentioned those particles, ghost particles. They are produced in the core during the nuclear fusion. They are one of the residuals of nuclear fusion. There is photons, positrons, and neutrinos. And neutrinos are there are lots of them. Lots of them are emitted by the sun constantly. And they are very, 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 very light particles. For a very long time, we even thought that they were like photons. They didn't have mass. It has been demonstrated very recently that actually they have a very, very tiny mass. And those neutrinos are almost like the photons. They are really going through almost everything. And on Earth, if we want, so if I just raise my hand like that, I'm constantly having neutrinos going through my hand, coming from the sun constantly, and the number of them is something like a few hundreds per nanosecond or few thousand per second. So we constantly have those flux of neutrinos coming from the sun that is going across ourselves, and they are not stopped almost by anything because they don't have mass. So they are particles with a very, very tiny mass. So the best way for us is to use very thick layers of lead, for instance, to stop them. And if you probably have heard about those particle accelerators or things like that, there is an experiment in South Pole, Antarctica, called Amanda. This is trying to detect those neutrinos. The problem with the neutrinos, they are very difficult to stop. Some of them can be stopped, but it's very rare. So what the physicists have done is they just within the core, within the ice of Antarctica, they have put detectors to form 1 cubic kilometer. So for 1 kilometer by 1 kilometer by 1 kilometer. So 1 cubic kilometer, and every 100 meters they put a detector. The advantage when it's buried through under the ice is because if you have the Earth here, the South Pole is here, and the neutrino is going from the North Pole, it has to cross the whole Earth before hitting the detector, which is beyond it. Okay, so those neutrinos, if you're the configuration when you have the South Pole here, the North Pole there, and the Sun here, the neutrino that is coming from the Sun has to cross all the Earth before reaching the detector. And during this process, it slows down, so it's easier to catch them. However, this experiment is there since a decade now, and managed to catch very, very few neutrinos, a handful of them. But we can catch them. It's very difficult, but we can catch them. And neutrinos tells us a lot about the Sun, actually the very internal core of the Sun, because they are produced by the nuclear fusion inside the core of the Sun. So it tells us exactly what kind of fusion is happening inside the Sun. And unlike the photons that are bounced inside the radiative zone, bounced by the particle of gas, neutrinos are going straight through it. So the neutrinos that we're catching now were emitted by the Sun nuclear fusion very, very recently. So they tell us a lot about, to give us a lot of information about the nuclear fusion within the Sun. So just to show you a picture of those two ways of doing measurements of the Sun's properties, this is heliosismology. So actually, as I mentioned to you, it's not pulsating this way. It's actually places that are going towards us and places that are going away from us. So it's just deforming constantly. And this is true for all the stars. So heliosismology, we start to propagate this idea to other stars nowadays. But of course, it's easier from the Sun because it's closer to us. So the red and blue patches represent regions of solar surface that are receding inward and bulging outward blue. And what we can learn is that if we do an analogy with a seismic wave in Earth, one wave can go from one of these cells to another. Okay, there are different paths of waves within the sun. So it's crossing different layers. And if you take the relationship between this cell here and the cell here, you just do a very shallower study. But if you correlate this cell here with a cell that is the other way around, you can do a very, very long distance study. And the propagation wave between those different cells can be studied in details. And it tells us what is the density, what is the gradient of density, and etc. And lots of information about the internal structure of the sun. Exactly the same way we're using it for probing the internal structure of Earth. And for the solar neutrinos, so remember this is the chain reaction I mentioned to form helium from hydrogen, 4 atoms of hydrogen, and 1 atom of helium at the end. And every time in this reaction you have neutrinos formed. At this phase you have neutrinos formed. And neutrinos, once again, they don't bounce back like photons, like I showed you. They could just go through it straight. And those neutrinos can only be produced in nuclear reactions. Well, there are slight complications, but I don't want to enter into details. But what we have, thanks to neutrinos, if you look at the neutrinos coming from the sun, is we have a direct probe of what is the nature of the nuclear fusion inside it, where it happens, how fast it happens, what is the rate, etc. So by studying the neutrinos, we probe the internal part of the sun. That's more or less how we know the temperature at the center of the sun. And actually, the first neutrino has been discovered in the late 90s, and Ray Davis, American physicist, got the Nobel Prize in 2002 for detecting the neutrinos from the sun. So the internal structure up to the surface of the sun is difficult to really understand, but we start to have probes thanks to those different techniques that I mentioned. The upper layer after the surface, what we call the surface, like we call the atmosphere. You remember Earth, we have the crust, the upper layer, but above it there's still atmosphere, there is air. And our atmosphere has different layers and composition as well. The analogy with the sun exists as well. So when you reach the surface, what we call the photosphere, the chromosphere, you still have an atmosphere of the sun. So there are different layers. So here we have the core, where the nuclear fusion happened, the radiative zone, the convective zone. Then we have the photosphere, the chromosphere, and the corona. So the photosphere is what we call the surface. It's the thing that we see the most. It's the brightest. This granulated surface with and there are several things I've mentioned in a minute, describe in a minute, like sunspots and faculas. This is the photosphere. This is where the photons that we see are emitted. So the temperature is the temperature of the blood body we measured, 5,800 Kelvin. So actually, when we talk about the surface of the sun, is this part here, the photosphere. Then there is an upper limit, a thin layer, 1,000 kilometers thick, we call the chromosphere. And the chromosphere is hotter than the photosphere. So what happens here, it's very hot here, it's getting cooler, less dense, up to the chromosphere. And then the temperature starts to rise again. These gases start to be far less dense than inside the sun, but far more hot. So it's rising from the 6,000 Kelvin at the surface to around 10,000 Kelvin at the upper limit. And there are lots of things happening in this place I'll describe to you in a minute, like spicules, filaments, prominence. So you remember when I showed you the first picture of the sun, we have this ejection. Usually these ejections are staying within the chromosphere. And the layer is called the corona. So we have lots of pictures of the corona. It's very extending, can go very far. Depends, we don't really know the limits anyway. And there are holes, and this is from the corona that the winds, stellar winds, solar winds are coming. It's a very, very, very low density of particles, but very, very high temperature. I told you several times when we were discussing about the Earth that the solar winds that are coming towards us from the sun are extremely, extremely dangerous for us. This is produced by the corona, so very high temperature. And actually, we still don't really have a clue why the temperature is so high. Something linked with the very low density, but we still have different theories to explain why the corona is so hot. So if you look at the photosphere, so once again, this is this layer that is the surface we're measuring. You can see that actually so this is degraded, but beyond the granulary features, the granulation of the surface, you can see different other features that we call sunspots mainly. So you probably, if I don't know if you ever have done this experiment, but if you take a picture of the sun, especially do it this summer, I'll explain to you why, but you just take a picture of the sun or project the sun through a telescope on a white paper, you will see that there are many of those black spots, sunspots, and it's known since a very long time. Actually, Galilei himself noticed that there were sunspots. And this region can be very extended. And particularly this year, there are a lot of them. Many, many, many sunspots. So then the chromosphere, I'll come back to explain to you what they are. Then the chromosphere, so here we mask out the photosphere, and this is this nebulous white-ish, it looks like atmosphere actually, around the sun. Sometimes it's more extended, you have a protuberance, here it seems seemingly ejection around there and there and there. And those features are just around it. And then you have the corona, I'll show you a picture later. So, when you look at the photosphere, you have those black spots, and you have other features that we call these kind of filaments. So this is a close-up picture of the sun, and so you see the granular region, but you really see those black spots here, and those things looks like filaments. We call them spikles as well. So many filaments that and those filaments and spikles are actually cooler gas. So they are a bit less cooler, so they are a bit less bright. You remember, if you look at the Boltzmann law, Stefan Boltzmann law. So they look darker because they are a bit cooler. They are a bit less bright. So you have the very bright parts are hotter, and the darker parts are cooler. And those filaments are getting, so this phenomena, they are getting cooler because they are actually ejected. So they are on the surface and they are ejected, so they are cooling down. They are very, very bright in H alpha actually. And usually those phenomena last about 5 to 15 minutes. So you just have a burst of matter going out from the surface and falling back again. That's creating those filaments. Sometimes, when the sun is particularly active, you can see a lot of them in one place. So these things jumping from there to there and there to there. And then this is a picture of the corona. So here you have a prominence which happened in the chromosphere, and the corona is this thing, and you see that those features are what we call solar winds. So they are very extended, very large scale, and going very far away from the surface of the sun. And sometimes the corona is very, very quiet, and sometimes the corona, like this year, is very, very active. And you can see coronas during total solar eclipse, for instance. So if you have the chance to see a solar eclipse during an active year, then you will have very, very bright corona features. So actually, they are not emitting light by themselves, they're just reflecting light coming from the sun. Okay? So these very, very low density, high speed particles that are reflecting light from the sun and coming towards us. So those streams are slow solar winds that leave the suns. So you start to get the picture. Our sun is actually can be very active. So we can have lots of flux of matter, of very high energy particles, or even hydrogen, that is emitted directly from the surface of the sun. So this is the corona, another picture taken by corona, but this time in X-ray, so very high energy photons. And this shows us, X-ray shows the structure that are very, very hot. So you see those bright things are actually active jets or particles that are emitted from the surface of the sun at very high temperature. So our sun is actually very, very active. And I mentioned that already. There are several cycles. There is a cycle, so the activity is not constant. So let's go back to those different features and try to understand what they are. So let's start for the most simple ones, the black spots, the sunspots. So actually, it's not since a very long time now when at some period of a year, every 12 years more or less, you have cycles of production of those sunspots. And at some times, the sun can present many of them. And those things can be very extended or very small. And you can have many of them. Actually, the sunspots are cooler part of the surface of the sun. So once again, as they are cooler, around 4,000 Kelvin, they look very dark compared to the surface. It's 2,000 Kelvin cooler than the surface. And they can be very, very big. Remember, the sun is massive anyway. Some of them can be even bigger than the size of Earth. So what are they? Well, our best guess, and actually it's more than a guess now, the best explanation for those is magnetic fields. So I haven't mentioned magnetic fields yet, but you remember the Earth is generating, like Jupiter and all the gaseous planets, a magnetic field. Here you have this big ball of gas that is very, very hot with a nuclear power plant at the center. And actually it's a dynamo the same way. You have lots of fluids. Remember, I mentioned that at the start, and it starts to get its importance. The equator of the sun is doing faster than the poles. So you have this dynamo effect. You remember I told you to generate a magnetic field, you just take an electric charge, a liquid, and make it rotate. And if you make it rotate fast enough, you're generating a magnetic field. Exactly what happened to the sun. So the sun is a very, very big dynamo with lots of magnetic fields. But some of the magnetic fields can get trapped, and smaller magnetic can get disconnected. So what those sunspots are is actually that they are magnetic fields that are going from one to another. It's small-scale magnetic fields. So there is the big dynamo, but at some point, one magnetic field of the big dynamo gets distorted. I'll show you the trap in the sunspot. So those sunspots are just matter that is ejected from the surface of the sun, from one sunspot to another, due to magnetic field. So the matter is following the magnetic field and following the other way around. So these magnetic fields are up to 1,000 times stronger than the normal solar magnetic fields around those sunspots. And they can be as large as 50,000 kilometers. And those sunspots vary, they change places, they appear, disappear, and typically they can stay for several months. And this is the example of a large, so these are the two sunspots, okay? And you see that there is a large protuberance, ejection of matter that seemingly is coming out from that sunspot, and it's falling down. And probably if you take a picture later, you will see it fall down there. So what's happening here is that you have a magnetic field between those two sunspots, and the matter is ejected and following the magnetic field. Another example, I see from cross-section, you see that these are ejection active sunspots, seeds at the sideways. So here you have a sunspot, and you see the same picture, but as seen by the above. And you see the matter is ejected and falling further. So there is a very, very strong correlation between the presence of sunspots on active regions. If you take a picture in the visible and picture in the ultraviolet reveals where those ejections are placed, so the activity, you see that there is a direct correlation. Here you have lots of sunspots, lots of activity. Here another sunspot, lots of activity. Here a third sunspot, lots of activity. So there is direct correlation between where those sunspots are and what is the activity of the sun. And as I mentioned, the sunspots are always in pairs. You always see two sunspots. They can be spread. They can be very far away from the other or very close one to the other, but they're always going on pairs. You're always to have a pair number of sunspots on the surface of the sun. So they're exactly like a magnet with a south pole and a north pole. And you see here, you really have the field. You almost can see the magnetic field. This is the matter that is going from north to south. And you see that it's really following the shape of a magnetic field. And sometimes we can directly see the loop, so the connection between two sunspots, for instance. So we really have many, many evidences of that. So we can use different measurements of the magnetic field distribution on the surface of the sun and compare it with the sunspot locations. And well, once again, in red here we have the distribution of magnetic south poles, and in blue we have the distribution of magnetic north poles. And you see that the locations are corresponding where the sunspots are. And here you have two poles, and here you see that you have a north and a south. So those sunspots are actually just the evidences of the fact that you have very small magnetic field on the surface of the sun, and on the magnetic field of those on those very small magnetic fields, you have lots of matter that is ejected from one part to the other. So actually, as there is an ejection of matter, those sunspots get cooler. So that's why they are black. So you always have a couple of sunspots, a north and a south, and you have magnetic field going from north to south, and you have matter that is ejected following those magnetic fields. So the sun at some point can be extremely active, and 2012 is a very high peak of activity of the sun actually. So this is a picture taken in ultraviolet once again, and you see all these things are activity. And if I showed you the distribution of sunspots, you can guess that there are many, many sunspots around there. Right. So what happens? First, the idea is, remember that the sun is a big magnetic dynamo. Okay, you have a general north pole and a south pole of the sun, and magnetic fields are going from north to south. But there is a differential effect. I told you already, the sun's equator is rotating faster than the pole. Okay? So here you have faster rotation than on the pole. So it's creating a differential rotation. If you look at sunspots, for instance, those sunspots will move faster in that direction than the sunspots there. And now our best model and scenario is that this differential rotation is responsible for the magnetic activity of the sun. So it's known since a very, very long time that sunspots have cycles. And as early as the 19th century, people started to count a number of sunspots seen on the sun per day. So there is in Lyon, where I did my master in France, there's a very old observatory. It's 300 years old, and there are people that just monitor every day. The first thing they are going in the morning, they look at the sun. Okay, they count the spots and they note it, and they do that for 200 years. And so we have very accurate measurements of the number of sunspots on the sun, and as we can see, the number is varying a lot. And you can see that there is cycle. So there are years that there are a lot of sunspots, but years that are very, very small. And you see this cycle activity? It's exactly 11 solar years. So every 11 years, you have a peak of activity. A peak of number of sunspots. So at the maximum number, you have lots of sunspots on it, and the minimum number, you have none of them. And if you push to 2012, 2012 is one of this peak of activity. So this year, the sun will be very, very hot, very, very active. So this summer is going to be very hot because we have lots of solar wind coming from the sun. And if you want to plan a trip to the Antarctica to see the aurora borealis, it's probably the best year before next 11 years, because you will have lots of solar winds, so lots of auroras in North and South Pole. So if you want to go this year, or you have to wait for 11 more years. So, how all this happened? What happened, if you take one magnetic field, so the South magnetic field, and the magnetic North Pole and magnetic South Pole, you start to have one magnetic field that's going from north to south, following the surface of the Sun. But due to this differential rotation, the point that is there will turn faster than the point that is there. So your magnetic field will start to be distorted slightly. Okay? So it will be exactly like it's pulled by the center of the Sun on the surface of the equator. And it's so bad that it gets trapped after several rotations, it gets totally distorted. You see? It's totally distorted. So at the center it had time to do several tours, while at the outskirts it had rotated more slowly. So instead of having a magnetic field that is going in straight line, you have a magnetic field that's going around and around the Sun. And eventually, it's so distorted that it gets disconnected. It breaks down. Instead of having one magnetic field going from north to south, you end up with a totally distorted magnetic field, and at some point it just breaks down. And when it's breakdown, it's forming a pair of sunspots. That means you have a magnetic field going from one part of the surface to another part of the surface. Instead of going from north to south, it's going to a closer pair of poles. So it's creating two poles. So then you start to have lots of activity, because you have very strong magnetic field that is pushing away some matter and it's falling down somewhere else. And after a while, it's getting so messed up and so distorted that those magnetic fields, because they are very small, they don't stay long. They disappear after a few months. So after a while, all those small magnetic fields will disappear. And then you end up with a magnetic field that is straight again, but going the other way around. Okay? Once again, at the start, you have the Sun with his very nice magnetic dipole, north and south. But due to the differential rotation, the fact that the equator is turning faster than the poles, then your magnetic fields start to be distorted. And then eventually, they get so messed up that they break down at some places, creating some pair of sunspots. Okay? So it's taking more or less 5 years, 5.5 years for it to happen. And then those sunspots, those magnetic fields disappear, and after 5 years again, okay, this process, because it's so break down that it starts to disappear, after 5 years, you end up with a magnetic field again that is straight, but in the other way around. And then you take 11 years, and you have cycles every 11 years. Why it's upside down? Okay. All right. So actually, we don't really know, but our best guess is that because the field gets totally destroyed. Yeah, because you start with a magnetic field that is very straight and clean like that, and you make it rotating, and you create small. It breaks down. Instead of having one magnetic field, it breaks down, and you have many of them. Yeah. And actually, I don't really know the answer to that. But as an effect of that, at some point, you have an inversion of polarities. I really don't really know the answer, to be honest. So I don't know. But it's a fact. It's turning. So you start with a magnetic field that is going from south to north this way. It gets distorted, and after 5 years, it has a peak of activity. So that means you have many small fields. They get destroyed with time, and after 5 years, 5 years later, you get a magnetic field that is cleaned. And then, due to differential rotation, it gets messed up again, and then you come back to the original. So it's 5 years, and here it's 11 years. So, if you take a picture of the Sun every 11 years, you will really see the cycle. So this is a quiet phase in 1996. Then year after year, you see the increasing activity on the surface. And 2001, you have a peak of activity. Then it's decreasing again up to 2006. And after 2006, you do another round. And 2012, this year, you will have a peak of activity. And so on. It keeps going. So we have alternance of quiet phase and active phase. So this magnetic activity and sunspot is creating those flares and prominence. So the main part of them are those filaments. They get just stuck in the chromosphere. But in some cases, when those magnetic fields are quite large, you can have projection that is going far above. And eventually, so when the two sunspots are very close, you have matter going up and down like that. And these are creating those filaments we see when it's staying in the chromosphere. But if the sunspots are far away one from the other, the matter can go very far away. Okay? And eventually, it's disconnected. It's just not come back. So the matter is ejected, and because it's going very fast and very high, it's not even goes back anymore. And it's just ejected from the surface of the sun. So it's creating those flares, what we call flares. So at very high one are called prominence, and when they just get disconnected and move away, we call them flares. And they're also probably the origin of solar winds. So the sun is constantly losing mass because of this. It's just ejecting matter in interstellar medium all the time. So these are nice pictures in far UV again of this prominence, so this ejection that are following those very, very strong magnetic fields. And another one here, it's pretty nice, you can see the reconnection. So given one sunspot, so usually sunspots are grouped in packs, so you may have several of them. It's very active like that. Once again, another one. Solar filaments that are lift off. And sometimes it's so strong that you just have a massive eruption and it never comes back. And when I say massive, look at the size of that thing compared to the size of Earth. Okay? That's pretty big. So imagine that those things that are coming toward us, those flares are coming toward us at very high speed, and they're very hot. And they're far bigger than Earth. So fortunately, we have our magnetic field to protect us from that, but that's very energetic. And those eruptions, those flares, when they are emitted, it's creating a shock on the surface of the sun and creating those sound waves. So when this thing is so energetic and so dramatic that is actually creating a shock wave on the surface of the sun. And at very large scales, we have what we really have the corona, or the crown. Corona is coming from crown. Latin. So in a peak of activity like this year, you see 2006. It was quite quiet 2006 actually. No, because it was produced in 2006. It's probably taken in 2001. You have a very, very important solar wind event. Okay, mass ejection. So the sun is not this quiet place at all anymore every 11 years. And it's emitting a lot of matter and ejecting lots of matter in the interstellar medium. So we have those solar winds. It's constant flow of particles that are coming from the sun at very high speed, 300 to 800 kilometers per second. And those things, of course, it depends of the peak of activity, but it's constant. We always have a flux coming from the sun, but during those years with very high activity, of course, the flux is higher. But in average, we estimate that the sun is losing mass of 10 to the 7 tons per year. So it looks big, but actually it's 10 to the minus 14, so 1301 mass per year of its own mass per year. So in other words, it will take 10 to the 14 years for it to exhaust its mass. So it's not really a problem for the sun. So this is the kind of emission that you can get. This is the this solar winds ejected here. But fortunately, I mentioned that Earth has a very strong magnetic field, and when you have those flares that are coming at high speed towards us, so it's very hot and it's going very fast, but those flares are shielded by the magnetic field of Earth. And the same way, because there is this constant flux, the magnetic field of Earth is distorted. But some parts of those particles manage to follow and be trapped in these magnetic fields here and end up in the poles, and they are originating those borealis, aurora borealis here. So this one is pretty spectacular. So if you want to see that, you have to go north and south, and well, you can see them even lower sometimes. Always have to go northern or southern, but you can observe them. You don't have to go to the south or north pole exactly. You can see them from lower, especially this year. We'll probably see some from Northern America. So there is a very strong activity of the sun, and it's driven by these magnetic fields. So the magnetic field is generated by differential rotation of the sun, and this differential rotation is also trapping the magnetic fields and distorting it and creating these sunspots. So you will have very active regions associated to those sunspots carrying very strong magnetic field locally, up to 1,000 gauss. So prominence will be a part of the solar plasma, part of the solar mass that is trapped in magnetic field and is arching away from the surface of the sun. So we can have very, very violent eruptions of magma coming from the sun, equivalent to several billions of hydrogen bombs. And this ejected plasma is shaking Earth's magnetic field, distorting it, and creating magnetic storms. So to finish, and come back to something we discussed about a few weeks ago about the climate change. The sun is also having a very strong impact on our climate. Imagine that every 11 years you have lots of energetic particles that is coming toward us. So it will hit up our atmosphere. So that's why people are planning, forecasting a very hot summer this year because of the peak of activity of the sun. So there is a large number of charged particles that are ejected from the sun coming toward us, creating geomagnetic storms and auroras. And those storms here reach Earth in several days. So the irradiance variations of the sun are probably triggering climate change as well. And actually there is a very interesting historical event. This is once again the number of sunspots with years. I mentioned that cycle of 11 years. So people are monitoring. And you see that beyond the cycle of 11 years, there is another more large-scale cycle. There are years, a couple of years when it's lower, and some of that is higher. And we don't really completely understand why. However, we have noticed that for 50 years, in the 17th century, the number of sunspots has been recorded very low. And we have tracks of even before that, and it was back to this normal. So these 50 years, we just don't really understand what happened, but the activity of the sun was very, very low for around 50 years. It's something that we call the Maunder minimum. And we know that this had a very direct impact on Earth. Because during this 50 years, we have recorded very, very cold winters, unusually cold winters during 50 years. And this is a painting of a lake that is frozen during summer. I think it's Dutch, so Northern Europe. So for those 50 years, the temperature very, very, very low. So there is a direct correlation with the sun activity and the climate on Earth. But just to come back to what I mentioned a few weeks ago, when talking about climate change, keep in mind that it's far more complex than sometimes what media and politics want to tell you. Okay? So I'm done with the lecture on the sun for today. Do you have any questions?
So the ejection in the surface is sometimes will fall back to the surface of sun.
Yes.
And sometimes it comes solar wind.
Yeah. So it's linked together. It depends on the strength of the magnetic field. So you can imagine that if the magnetic field is broken in very small pieces, so two sunspots will be very close one to the other. So the magnetic field will reconnect very rapidly. So the matter will fall back very rapidly. But if the sunspot, the magnetic field is broken for a long distance, and sunspots are very far away one from the other, and if this magnetic field is very strong, then you have lots of matter ejected. And sometimes it's just ejected and never comes back. It's breakdown from the magnetic fields. So this is at the origin of those flares that are coming up in solar winds. Okay, thank you very much.